This is Chapter 8, Section 2. We're going to look at shift and equilibrium within a system. And this section is very wordy, and it's all about what can we do to change the shift and equilibrium. And we'll talk about several factors that can affect equilibrium. So, predicting the shift, we're going to look at pressure, concentration, and temperature as ways of changing equilibrium. Starting off with LaChatelier's principle. So you're going to want to write down LaChatelier's principle. Says if a system in equilibrium is subjected to a stress, and again, those stresses are the three things we just looked at up top, then the equilibrium is shifted in the direction that tends to relieve the stress. Kind of like when we were talking about entropy. Entropy is the state of going to randomness or chaos, and we're trying to get away from the randomness and chaos, so we want to relieve the stress. This is going to be true for all dynamic equilibria, chemical as well as physical, and changes in pressure, concentration, and temperature. We're going to use those to illustrate LaChatelier's principle. So again, definition, make sure you get it down. In this first video right here, it is going to talk about, and I'm just going to do this quickly. Don't need just a ton to go with this because it will be described here soon. If you increase the temperature, then you have more kinetic energy. So if you decrease the temperature, less kinetic energy or less movement. If we increase the pressure, then we will reduce the moles of whatever side, reactant or product, where we have decreased the pressure. And on this next video, the main components of it are if you increase concentration, then the reaction will go to the side with less concentration. So it's going to want to move to a side of less concentration. And if we increase the pressure, where we said it wants to reduce the moles, again, you want to go to fewer moles that will reduce the stress of your system. So we want to reduce pressure by having fewer moles. Change in temperature. A change in temperature can be endothermic or exothermic, and we will look at temperature. So you might not need to write down all of this, but we will look at some important parts. So a change in pressure affects only equilibrium system in which gases are involved. So a change in pressure, you got to have gases involved if you want to do this. For changes in pressure to affect the system, the total number of moles of gas on the left must be different than the total number of moles of gas on the right. So if you're looking at, for instance, the one that we just had, the nitrogen, this was in section 1, plus oxygen yields 2 nitrogen monoxides. Well, as I look at that, that is 1, 1. Well, that's a total of 2. We have 2 on the other side. So if we're talking about a different number of moles of gas, you've got to do something to change the moles of gas there. And an increase in pressure is an applied stress. So increase in the concentration of all species. If you increase the pressure in the system, can reduce the total pressure by reducing the number of molecules. So that last part is also important. It just describes a little further what I was pointing out of what would have been in the previous video. So in this slide right here, it is talking about the Haber process. I think it's important that you know this term, the Haber process. Sorry about that. Loud for me too. But anyways, within the Haber process, it is the synthesis of ammonia. So they have a specific name for the making of ammonia gas. And it's where you have your nitrogen and hydrogen gases combining to give you ammonia gas. Notice this one, the number of moles is different. We have 1 plus 3. That's where our 4 comes in. 2 moles of ammonia, you have our 2 right here. So when we do apply our pressure, the equilibrium will shift to the right because you have less number of moles. And by shifting to the right, the system can reduce the total number of molecules, which will decrease the pressure. So if you can reduce the total number of molecules, you will decrease the pressure. So this is saying that even if you have a change in pressure that shifts the equilibrium position, it does not affect the equilibrium constant. But what if you introduce an inert gas, such as helium? Again, an inert gas, its presence is there, but it's not going to react with anything that's around it. The presence of it, though, will increase the total pressure of the vessel. So you can add a gas that won't react with anything that's in it, such as helium, but it'll still increase the total pressure, but it does not change the partial pressure of the reaction gases that are present. So we do have a thing for partial pressures too. So this right here, increasing the pressure by adding a gas that is not a reactant or product cannot affect the equilibrium position of the reaction system. So it's not going to do anything to change your partial pressures of the actual gases that are doing the reacting, so it will not affect the equilibrium position of your reaction system. So that dealt with pressure. Now let's look at what happens if you change the concentration. If in this example you had an increase in concentration of the reactant, which would be a stress on the equilibrium system, it's going to want to shift toward your products. That's an increase in a reactant A, will create a stress. To relieve it, some of the added A reacts with B, and it wants to shift towards forming your products. Until equilibrium is reestablished with a higher concentration of A than before the addition and a lower concentration of B. So in this part right here, once equilibrium is reestablished, you will have a higher concentration of A and a lower concentration of B, because again, you added more A to the system. If you change the concentration, though, it will have no effect on the value of the equilibrium constant. That was a lot like the pressure we looked at. Any changes will have an equal effect on the numerator and denominator when you're going to do your calculation, so it's just tit for tat. The concentrations of pure solids and liquids do not change. So pure solids and liquids do not change and are not even in the equilibrium expression anyways. So when you add water to a system, and you're talking about acids and bases, the equilibrium equation, it's not included in the expression anyhow. So even if you add water, it's not going to change our expression. So we're going to look at this example here. We've got calcium carbonate breaking down into calcium oxide and carbon dioxide gas. Notice I see some things in the solid state, and carbon dioxide is the only thing in the gas state. So let's look at some changes and how they would affect this. There is the equilibrium expression. So K equals the concentration of CO2. That's the only thing that's in gas phase within this one that we can even use, and it is raised to the first power because that is a balanced reaction that you see up top. So high pressure will favor the reverse reaction because the higher the pressure, it wants to move away from high pressure. Well, pressure, in this case, is only going to affect what's in the gas phase, so it will want to move away from it. A low pressure will favor the formation of carbon dioxide gas because it is a gas, and because you see our two solids there, changing their amounts will not change the equilibrium concentration of carbon dioxide gas because they are not included in the expression. Reversible reactions are exothermic in one direction and endothermic in the other, and that could be either way. So the effect of change in the temperature of an equilibrium mixture depends on which of the opposing reactions is endothermic and which is exothermic. So you need to know which direction is endothermic, which direction is exothermic, and then we'll look at the changes. So the addition of energy in the form of heat will shift equilibrium so that energy is absorbed. That means we are going to favor the endothermic reaction. So if you add energy, it will shift equilibrium so that energy is absorbed, which favors the endothermic reaction. So just the opposite will be true. The removal of energy will favor equilibrium so that energy is given off, and it favors the exothermic reaction. So make sure you have these two down as far as changes in temperature. And in this right here, a rise in temperature does increase the rate of any reaction. We did say that our equilibrium constants, they do change based on temperature. So the volume of the equilibrium constant for a given system is affected by temperature. We did already state that earlier, but that is important. So looking back at the Haber process again, notice this time they give us the energy that's associated with it. And in this one, it is considered exothermic. How this is placed, it says plus 92. So they are adding this as a product. Because they're adding it as a product, it will be exothermic the way it is stated right here. So it is exothermic. A high temperature will favor the decomposition of ammonia. Ammonia is our product, which favors the endothermic reaction. So it would go back the other way. At low temperatures, the forward reaction is too slow to be commercially useful. So the temperature used represents a compromise between kinetic and equilibrium constants. So again, the temperature will affect what is going on right here. This is showing you nitrogen dioxide breaking down into dinitrogen tetraoxide. And you can see just by looking at the colors of the gases you have right here, the equilibrium is shifting based on how dark that gas is. Moving on to another direction, catalysts. Catalysts have no effect on relative equilibrium amounts. They will only affect the rate at which equilibrium is reached. So, catalysts have no effect on the equilibrium amounts, but they do affect the rate. So, catalysts tend to increase the rates of the forward and reverse reactions in a system by equal factors. Therefore, they do not affect K. They do not affect your equilibrium constant. You're going to want to write all of this down here. This is talking about ions in solutions. So if you do have compounds formed by a chemical interaction of ions in a solution, they appear to go to completion in the sense that ions are almost completely removed from solution. But that second part is important. The extent to which reacting ions are removed depends on possibly two things. It will depend on the solubility of the compound formed, and if that compound is insoluble that's formed, then the reacting ions that are being removed will depend on the degree of ionization. So, for instance, if you have our acids, our strong acids that 100% ionize, versus, say, a weak acid like acetic acid, which only ionizes about 5%, that will change how your reaction will proceed. And we'll look at an example. In this reaction where carbonic acid is breaking down into water and carbon dioxide gas, it says this reaction goes practically to completion. Notice it's just in the forward direction because one of the products, carbon dioxide, which is a gas, escapes as a gas if the container is open to the air. So if your system is left open to the surroundings, in this particular one, the forward reaction is what's going to happen. And in this one, formation of a precipitate, so you've got, this would have started off with sodium chloride and silver nitrate. They have broken all of this down into, we're already looking at an overall ionic equation right here, would have broken down into sodium nitrate, which is still aqueous, but in this double replacement reaction, the silver chloride that was produced This is in the solid phase. That was the precipitate that happened. So when I look at this overall ionic equation, again, sodiums cancel, the nitrates cancel, and you got your silver chloride, which is a precipitate. The following is what it needs to be pointed out. If chemically equivalent amounts of the two solutes are mixed, so that's your sodium chloride and your silver nitrate, almost all of the silver ions and chloride ions combine and separate from the solution as a precipitate of silver chloride. Silver chloride is only very sparingly soluble in water, so the reaction will thus effectively goes to completion because an essentially insoluble product is formed. So again, the forward reaction here is what's going to take place because you are creating a precipitate which basically is insoluble. In this reaction, we're looking at the hydronium ions from aqueous acids and hydroxide ions from aqueous bases result in the formation of water molecules which are only slightly ionized. So water itself, you can put that into the liquid phase here. Water has a very, 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 very low ionization that it can do. It looks like we had hydrochloric acid and sodium hydroxide. Originally starting off, if they're talking about acids and bases, so hydrochloric acid, sodium hydroxide, they've broken those ions down right here because this could have been listed also to think of the hydrogen ion going with your chlorine. And water is formed during this neutralization reaction that's only slightly soluble. And given that's the case, there's your net ionic equation. And the hydronium ions and hydroxide ions are almost entirely removed from the system because they're forming the water. And the reaction effectively runs to completion because the product is only slightly ionized. So again, once water is formed, it will barely ionize itself. Now, moving on to the common ion effect. Write down this definition. It is where you have the addition of an ion common to two solutes, it's what you're reacting, brings about precipitation or reduced ionization. So another example, hydrogen chloride gas, that's your hydrochloric acid, is bubbled into a saturated solution of sodium chloride. There you have it right there. So hydrochloric acid or hydrogen chloride gas is bubbled into a solution of sodium chloride, and you see they've got your two different reactions going on here. You're going to want to write those down. The hydrogen chloride will dissolve in sufficient quantity. It increases the concentration of chloride ions in solution, which is a stress on the equilibrium system. The system can compensate, though, by forming some solid sodium chloride, which precipitates out, relieving that stress. So you got your sodium chloride, it will dissolve into sodium and chloride ions. And the new equilibrium has a greater concentration of chloride ions, but a decreased concentration of sodium ions. So I did go backwards just to point out that last part that was said in the slide. Notice in both of these reactions, you have the chloride ions that are being produced. And so it says the new equilibrium does have a greater concentration of chloride ions, but a decreased concentration of sodium ions. Because again, the chloride ion is in both of these, but you do have your sodium that wants to react with your hydronium ion. In this reaction right here, again, talking about the common ion effect, if we're looking at our two reactants, so you've got a reactant here, they're both in solution because it's barium and sulfate ions in solutions on the left, and then you've got your sodium and sulfate ions in solutions on the right. But when those two come together, and sulfate is our common ion that we have with both of these, so sulfate is the common ion. This reaction will happen to give us solid barium sulfate. If you think of your activity series, barium is more active than sodium, so the barium will take its place over sodium. This is also a double replacement reaction, and the solid barium sulfate is the precipitate that is going to be formed. So this reaction does take place even with a common ion between the two. So we have one last example here. The common ion effect is also observed when one ion species of a weak electrolyte is added in excess to a solution. So what if you have one ion species of a weak electrolyte that is added in excess to a solution? So they are showing you acetic acid, which is considered a weak electrolyte. It's a weak acid. Notice it's a reversible reaction here. It'll break down when it mixes with water to the hydronium ion and the acetate ion. If you add small additions of sodium acetate, again, the common ion would be that acetate ion. If you add a little bit of sodium acetate to the solution containing this acetic acid, it will increase the acetate ion concentration. So it will increase the concentration of the acetate ion. The equilibrium will then shift in the direction that uses up some of the acetate ion, and more molecules of acetic acid are formed, because that means it's going to go over here to the reverse reaction, and more molecules of acetic acid are formed, and the concentration of hydronium ions is reduced. So again, hydronium ions being reduced, that is our hydronium ions. So if we did add a little bit of sodium acetate to this, the common ion is the acetate ion. It will move in the reverse direction to reproduce some of our acetic acid. So in general, the addition of a salt. The salt in the previous example was the sodium acetate. And the addition of a salt with an ion common to the solution of a weak electrolyte reduces the ionization of the electrolyte. That is the end of section 2.